Hi. Well, it seems to be getting colder and colder in Moscow, and meanwhile we continue our discussion of capacitors. So what is a flat capacitor? Two plates parallel to each other, made of metal or some other conductor, and charged to some positive charge one plate and negative charge another plate. In order to charge a capacitor, you have to take the charge minus Q from the lower plate, which was initially neutral. You have to take this charge and bring it to the upper plate. So that will be the charge of the capacitor. If we know the distance between the plates, and if we know the field intensity or the field strength inside the capacitor, then we can easily calculate the potential difference or voltage between the plates of the capacitor. That will be field strength times distance. We discussed it last time, and also we discussed that the charge of the capacitor is proportional to the potential difference. The larger the charge, the larger will be the potential difference between the plates. And so people introduced a coefficient of proportionality, which is generally denoted by C, and this coefficient is called capacitance. So this is a capacitance. Now we will discuss in a few words how can this capacitance be calculated for different sorts of capacitors, and how this quantity depends on geometrical shape of the plates of the capacitor and on dimensions of the capacitor. So the capacitance from here can be written as the charge of the capacitor divided by the potential difference. And the potential difference is just the field strength times distance between the plates. So we can put it here, field strength times distance. The distance between the plates is something that we can easily change by just shifting the upper plate up and down, up or down a little bit. So the distance can be changed. And the question is, if we change only the distance, will the charge of the capacitor change? Certainly not. The charge will be here. The number of electrons put on this plate will remain unchanged because we do nothing with this number of electrons here. The charge will remain the same. So if the charge remains the same on the upper and on the lower plates, then the field strength also will remain the same. The field strength and the charge will remain constant if we shift a little bit the distance. So from here we can derive that the capacitance is inversely proportional to the distance between the plates if all other parameters are kept constant. Also from here we can write the following expression. The charge on the plate may be expressed using the surface area of the plate and the surface charge density. I will denote this quantity by sigma. So the charge can be expressed as the surface charge density, that is the density of the unit area of the surface. And if we multiply this quantity by the surface, then we obtain the whole charge on the plate. So the charge can be put as the surface area times the surface charge density and divided by the field strength times d. What if we somehow change the surface area? Well, how can it be done? We can take another capacitor, well, practically the same. I will draw here the same capacitor with the same plates, the same distance between the plates, the same area, and charged as the first capacitor, absolutely identical. And what will happen if we just connect these two capacitors? This point will be connected to this point. We just merge them together. What will happen? First of all, the area of the upper plate and down plate will double, because the initial area was S, and then another area was merged here. So the area of the plates will double. Certainly the charge will also double, because the charge of this plate plus the charge of this plate will be the charge, the total charge. Yeah. But the sigma, this charge density, will remain the same, and therefore the field strength will remain the same. These two quantities will not change. The only thing changing in this formula will be the surface area. So from this fact we may conclude that the capacitance must be directly proportional to the surface area of the capacitor. And so from these two formulas we may deduce that the capacitance should be directly proportional to the surface area of the capacitor plate and inversely proportional to the distance between the plates. Also, we may do something more with this capacitor. We may fill the space between the plates by some dielectric substance. And what happens in this case if we fill the capacitor with some dielectric? We take a plate of dielectric and insert it here between the plates of the capacitor. What happens then? It's well known that in dielectric the field strength is diminished as compared to the empty space. The field strength in dielectrics, the field strength here inside the dielectrics, will be some smaller than the field strength outside the dielectric. So the initial field strength in the empty capacitor must be divided by some number like 2 or 3 or 5 or something like that. So we denote this number by the Greek character epsilon, and this physical quantity is called permittivity, dielectric permittivity. So this is a permittivity dielectric permittivity of the substance, of dielectric material, and it usually takes the values of not very large number like 3, 5, or 6, or 7, well, not very large number, but it's more than unity usually, and so that the field inside the dielectric is smaller than it was in the empty space before the dielectric substance was inserted here. Why does it happen so? What is the physics of this phenomenon? The physics is simple. If we draw the picture of this slab of dielectric substance, we can understand that there are molecules inside the dielectric substance, and these molecules in the external field will be polarized. Sometimes that happens. Without any external field, each molecule is absolutely neutral. If we switch on the external field, the molecule remains neutral, but the positive and negative charges inside the molecule are somewhat displaced in different directions. The positive charge in this case will go slightly up, and the negative charge will go down because of the forces from the external field. If the external field has this direction, and all the molecules will be polarized. of the molecules here on this surface. And these charges, displaced charges, will be compensated in the inner volume of this dielectric. They will compensate it, minus and plus compensated. But the charges on the surface will not be compensated. And the one surface will obtain some positive charge, and the opposite surface of the electric slab will have some negative charge, non-compensated charge, because the molecules are polarized in the external field. And these non-compensated charges will create their own field, which will be directed from the positive charges towards the negative charges. And that internal field of dielectric inside the dielectric will be directed oppositely to the external field. That will be internal field which will be directed oppositely to the initial external electric field. So that inside the dielectric, the external field will be diminished by this quantity, by the magnitude of the internal field. So that the net field or resulting field inside the dielectric will become smaller. And this fact is reflected by this formula. The field inside, the resulting field inside the dielectric is smaller, a few times smaller than the initial field that existed in this space before the dielectric substance was inserted here. So if we take into account this property of dielectrics, which can easily be understood if we consider molecular structure of the substance, then we can understand that if dielectric substance is inserted between the capacitor plates, then this field inside the dielectric will become smaller by epsilon times, and therefore the capacitance will become larger by the same coefficient epsilon. Therefore, the capacitance is directly proportional to epsilon, the dielectric permittivity of the substance placed between the plates, and directly proportional to the surface area of the plates, and inversely proportional to the distance between the plates. There must be some additional coefficient here, and I can tell you that this additional coefficient is very simple. If you carry out detailed calculations, you will obtain that the additional coefficient in this formula is the dielectric, is the electric constant, or vacuum electric permittivity, sometimes it's called. So the final formula will be this. The formula for capacitance of a flat capacitor. That is in the international system of units, when the surface is measured, surface area is measured in meters squared, and distance is measured in meters, and capacitance is measured in farads. So, in the course of electricity and magnetism, which you will study in the second course of studies at MIT, you will be able to derive this formula. You will be able to prove that this is absolutely correct. Let's consider a few examples. Suppose we have a capacitor. Which has a capacitance of 0.001 microfarad. And this capacitor is charged to a potential difference of 1 kilowatts. So what is the charge of this capacitor? Very simple problem, just to illustrate the calculations related to capacitors. So the charge, we have the formula for the charge. The charge of the capacitor is proportional to capacitance and potential difference. So we have the capacitance that's given and the potential difference is given. So we have to take here capacitance times the potential difference. Capacitance is 10 to the minus 3 power of minus 3, and microfarad. Micro means 10 to the power of minus 6, and 1 kiloohm is 10 to the power of 3, and so that will be in international systems, in international units, farad times volts, and that will give us the charge again in the international system units, and that will be coulomb, certainly. So in order to calculate it, it's very simple. We see that 10 to the power of minus 3 will cancel with 10 to the power of 3, and what remains here, 10 to the power of minus 6, that will be 1 microcoulomb. Such will be the charge on the capacitor, 1 microcoulomb. Also, it's interesting to calculate the capacitance of a round ball made of metal having radius r. Why such an isolated conductor has a capacitance? Because if you put some charge here on this ball, then it will have some potential, some electrical potential. The potential is measured relative to infinity. So I remind you, the definition potential of this conductor will be defined by the work done by the field if we take some small charge element and allow it to go to infinity. So the charge quantity times the potential of this surface will be equal to the work done by the field. And from this definition, this is a definition, we can define what is a potential. Potential of the surface of any conductor is the work which the field will perform if some element of charge is moved to infinity from the surface of this conductor, divided by this quantity of charge which will move to the infinity. So we can easily, based on this formula, on this definition of potential, we can easily find the potential. Of this sphere. And if we know the potential, then using this formula, we can find the capacitance of the conductor of the round sphere made of metal, because we know the charge and we know the potential, so we can calculate the capacitance of such a conductor. Well, we have already derived the formula that the potential of such a sphere is K, the charge placed on the sphere, divided by radius. And we know that also we know that the electric strength in this near the surface will be defined by Q divided by R squared. And we have to take this formula as definition of capacitance. And using this definition, we can derive that the capacitance of this conductor will be equal to the charge divided by the potential. And the potential is given by this formula. So we use this formula here, and we obtain the charge divided by K, Q, and the radius goes to the denominator. The charge will be cancelled here, and what we obtain, the radius divided by K. Now we may recall that K is equal to 1 over 4 pi dielectric constant epsilon 0, and so we obtain here 4 pi epsilon 0 radius. And suppose the radius is 1 centimeter. 1 centimeter. Then this quantity, if I remember it well, it's something like about 1.1 10 minus 10 by 1 centimeter. 1 centimeter is 10 minus 2 meters. And so that will give us in international system of units 1.1 minus 10 power and minus 2 will give us minus 12 power. What? Capacitance is measured in farads. So this is certainly minus 12 power is 1.1 picofarads. At this point, such will be very small capacitance of a sphere having radius of 1 centimeter. Very small capacitance. This may be, at this point, it's quite reasonable to explain the system of denoting different powers of 10. So if we have 10 minus to the power of minus 12, that will be picofarads or picoseconds or anything. And if you have 10 to the minus 9, that will be nanofarads or nanoseconds, etc., nanometers. If you have 10 to the minus 6 power, that will be micrometer or microsecond, etc. If you have 10 to the minus 3 power, that will be like millimeter, millisecond, etc. So all this is very useful to denote different orders of magnitude. When you have different orders of magnitude, it's inconvenient to say 10 to the minus 12 power. It's a long and inconvenient expression. It's much shorter and much more convenient to say picosecond or picofarad. It's also inconvenient to say 10 to the minus 9 power. It's much more convenient to say nanosecond or nanofarad and nanometer, etc. So people use these short words to denote the powers of 10. Another thing I wanted to discuss will be a simple question: what is the charge of a capacitor? Suppose we have a capacitor consisting of two parallel flat plates, and this is a conductor, this is a piece of metal, and we may put any charge on this conductor. Suppose we put a charge minus Q. Now this is also a conductor, a piece of metal, and we can put any charge here. Suppose we put a charge plus 3Q. What will be the charge of such capacitor? We need to know the charge in order to calculate the potential difference, for example. Or if we know the potential difference, we need this to calculate capacitance. So what will be the charge in this particular case? To find the answer to this question, we must recall how did we produce this charge of capacitor. We took it from one plate and brought it to another plate. That was the procedure. So by definition, the charge of a capacitor is the charge that will flow from one plate to another plate if we connect the plates by a conducting wire. Or in other words, if we short circuit the plates. If we short circuit, then some charge will flow from one plate to another. We don't know what charge will flow, but it's easy to calculate it. This charge will flow until the two charges on both plates will be equal. So we can derive this condition that the initial charge on the right plate minus the charge that went away after we short circuited the plates will be equal to the initial charge on another plate plus the same charge which we'll add here. From this equation, we can obtain that the charge Q is 3Q plus Q, 4Q divided by 2. Will be 2Q in this particular case. For this conductor, the charge Q of the conductor, the charge Q will be equal just to small q. Capital Q equals to small q. In general case, if one plate of conductor contains charge Q1 and another plate contains charge Q2, then the charge of this conductor Q will be equal to Q2 minus Q1 divided by 2. That is the charge of a capacitor when two plates have different charges. That's quite possible. Why not? We can charge this conductor. We can put any charge here, impart any number of electrons. We can make it larger or smaller. We discussed it last time. So the charge of a conductor is such a charge which will flow from one plate to another plate in case we short circuit the plates by some conducting bridge. We put here a conducting bridge. Short circuit, and what charge will flow from one plate to another? That will be the charge of a capacitor. Now we will consider another important issue, which may be called a connection of capacitors. Connection of capacitors. Suppose we have one capacitor of capacitance C1, which is connected in parallel to another capacitor of capacitance C2. What will be the capacitance of such a connection? The capacitance between points A and B. So, total capacitance of such a battery, such a circuit. Well, we recall the definition of capacitance. Total capacitance will be equal to total charge accumulated here divided by the voltage between points A and B. And the total charge can easily be assessed if we know the charge on the first capacitor and the charge on the second capacitor. Then the total charge will be just the sum of these two charges. Q1 plus Q2 divided by the total potential difference. And the potential difference will be the same as between points A, B, or on the first capacitor or on the second capacitor. The potential difference is the same. It will be between these capacitor plates, the potential difference will also be U and B. It's the same. We may denote it simply by U, and the same potential difference will be here. Because this is a single conductor and it has definite potential, because between the different points of conductor, potential difference is zero. We discussed it last time. A single conductor has the same potential. All the points have the same potential. And also this refers to the left conductor containing the left plates connected by this wire. This is a single metal piece of metal, and it has a definite potential, because potential difference between different points in a single conductor is zero. Potential difference is zero between any two points here. And so this part of the circuit has a single definite potential. And so if this has definite potential and this, then the potential difference will be the same between the left and right plates of any conductor if these conductors are connected in parallel. So the potential difference is the same, and what we have here is Q1 divided by U plus Q2 divided by U, and by definition Q1 divided by U, Q1 divided by potential difference is the C1, is the capacitance of the first capacitor. And by definition Q2 divided by U is the C2 capacitance of the second capacitor. So if we have some number of capacitors connected in parallel, the total capacitance of the battery will be given just by the sum of these capacitors. There may be more than 2, maybe 3 or 4, any number of capacitors connected in parallel. So you have to find just the sum of all the capacitors in order to determine the total capacitance of the battery. Another situation which we consider is the connection of capacitors in series. When capacitors are connected in series, that is one capacitor and another, and so we have to find the capacitance between points A and B, and the first capacitor will have capacitance C1 and the second C2. And then there may be several such capacitors. For simplicity, I consider just 2 of them, but you may consider more. It's not a problem, it's very simple. So what happens here? If we charge this circuit, if we put some charge here, plus Q, or some charge plus Q, then this plate will obtain charge minus Q, because the electrons will flow from here to here, because they will be attracted by this plus Q. The electrons will be attracted here to this positively charged body, and so they will charge this left plate by the same charge minus Q. And if these electrons went from this plate, then this plate will acquire the charge plus Q, again, the same as here. And so the same charge but minus Q will be here. So in this case, when the capacitors are connected in series, we come to the conclusion that the charge on each capacitor must be the same, because of the law of conservation of electrical charge. Electrical charge cannot originate from nowhere and cannot vanish. If some number of electrons went from this plate to this plate, then the charges will be equal by modulus, equal by magnitude, but here will be negative charge and the same but positive charge will be here, because charges do not vanish and do not originate. So in this case we have we can say that the total capacitance between points A and B again will be given by the same formula, the total charge, which will be Q in this scheme, divided by total potential difference AB. Total charge Q originates if we short circuit points A and B. If we connect these points with some wire, conducting wire, then the charge plus Q will go from here to here to cancel the minus Q. So this Q is just the charge of the battery in this particular case. And the charge is the same for each. The charge will be the same for each capacitor. What about the potential difference? Potential difference between points A and B will be equal to potential difference on the first conductor, on the first capacitor, that is Q1, plus potential difference on the second capacitor, U2. And now we can remember we can recall what is U1 and U2. U1 by definition is the charge on the first capacitor divided by C1, and Q2 is the charge on the second capacitor divided by C2. Well, the charges on the first capacitor and second capacitor are equal and equal to the charge between points A and B. So this can be cancelled, and what we obtain here is 1 divided by 1 over C1 plus 1 over C2. So, looking at this formula, we can easily understand, let's see, capacitor, total capacitance of this battery. It's better to write it in this way. 1 over C AB will equal to 1 over C1 plus 1 over C2. And so on. If there are more than two capacitors, then the formula will be maybe written in the same way to include all necessary terms. Why this is so? Because the charge is the same on each capacitor, and if we multiply this formula by Q, the Q will be the same here, and that will be the charge for each capacitor. And Q divided by C, by capacitance, is what you can see charge divided by potential difference is this capacitance, is the charge divided by capacitance will be potential difference. So this is potential difference on the first capacitor, and this will be potential difference on the second, etc. And this formula originates from the fact that potential difference between point A and B equals the sum of potential differences, the sum of voltages on each element of this serial circuit. So we obtain this formula for the series connection of capacitors. And another thing I wanted to discuss will be the energy of charged capacitor. The energy of charged capacitor. Suppose we have a capacitor charged with some potential difference U and charge Q. If we take some additional charge from here and carry it to another plate, additional small charge delta Q, we will perform some work delta A equal to the potential difference times charge delta Q. And the potential difference is known to be charge divided by capacitance. So if we take some charge and carry it to another plate against the field will perform some work. Or we will perform certainly some work to bring this charge to another plate, to increase the charge between the plates by some small amount, to increase the potential difference by some small amount. We will produce some work. Where does this work go to? This work is sure to go to some energy stored in the capacitor. By charging the capacitor, by taking more and more charges, we will increase the potential difference, and our work produced will go to increase the energy stored in potential energy stored in capacitor. So, in order to calculate this work, I suggest that we draw a sketch. We draw a graph of the dependence of potential difference versus charge. The potential difference is proportional to charge, so the graph will have this form. That will be the straight line. The potential difference between the plates is proportional to the charge of the capacitor according to this formula. So that will be the straight line. And if we have some particular charge corresponding to some particular potential difference, then where will be the small amount of charge on this graph? That will be small surplus to the charge, that will be delta Q. And so what is the potential difference multiplied by delta Q? The potential difference is the height of this figure, of this small parallel, small rectangle, and another side of the rectangle will be small increment in charge. So this product of U times delta Q geometrically will equal to this area of this figure, this rectangular figure. So that if we carry charges delta Q step by step, we will perform work denoted here graphically by such areas of these figures, and finally we will perform work which is equal to this area of this triangle, of this right triangle. So the work performed will be equal to the area of this triangle, the total work performed when we charge the capacitor, step by step taking small delta Q's, small charges from one plate and carry this charge to another plate. The work performed will be equal to the area of this triangle. And the area of this triangle can easily be calculated because this is a right triangle, this angle is 90 degrees, and we have to take one leg of triangle, which is Q, multiplied by another leg, which is U, and divide by 2. So that will be the energy stored in the charge capacitor. And I will put it in some other ways. So the energy is charge multiplied by potential difference over 2. The energy stored in capacitor. If we recall that U can be substituted by Q over C, then we obtain Q squared over 2C. That is another formula to represent the energy of capacitor. And also, if we take Q from this formula and express it as U times C and substitute here for Q, then we will have C U squared over 2. All these formulas are equivalent and all they can be used while solving problems if you need to calculate the energy of a charged capacitor. Now let us consider some simple problems in electrostatics. First problem, number 400. Let's go this way. Problem number 400. If only one charged body is available, can it be used to obtain a charge exceeding many times in absolute magnitude that which it itself has? Well, sometimes the translation into English is clumsy of this collection of problems. So we have some body charged, for example, to a charge plus Q. Some small body charged and having charge plus Q. And the problem asks, can we use somehow this charge to obtain a much larger charge on another body? That is, we have another body, another object, and we want to charge it so that the final charge of this body be much, much larger than the initial charge of this small ball. Can it somehow be arranged? The answer is yes. And the procedure is as follows. First, we must take another ball, which is fastened to the end of a rod, and this rod may be used as a handle, and this rod is made of dielectric or insulator, so that charges will never go away from this ball. And we connect this ball to the ground and carry this ball closer to the charged ball. And this initially charged ball may be, for example, hanging on a silk thread, so that the initial charge doesn't flow away, because this is also an insulator. So we carry this second ball closer to the first ball, and we know that the second ball will acquire some negative charge delta Q, due to electric induction, because electrons will be attracted here and will flow to this charge. They will be attracted by the by the positive charge here. The negative charge will flow here, and so this charge will acquire this ball will acquire some negative charge. And then we disconnect it from the wire, and this negative charge may somehow be placed on the second body. But the procedure to place it will be very peculiar. We make a small hole here, and we insert this charged ball inside and touch the surface of the sphere from inside. We know that when we touch the conductor, both bodies, the large sphere and the small ball, if they are in contact, they will form a single conductor. And we know that the charges in a single conductor tend to distribute on the surface of this conductor. So all this charge will flow away from the small ball and will be distributed on the surface of the large sphere. Then we take this small ball away from the sphere, from this hole, and repeat the procedure. Repeat it again. We connect the small ball with the ground, we earth the small ball and put it closer to the first charged ball, and then we observe how the small ball is charged, and this is charged by electric induction, and then we disconnect it, and then we put it again inside the large sphere, and again the charge which is here will tend to distribute and will be distributed on the surface of the large sphere. And if we continue this procedure for many, many times, then the total charge on the large sphere will turn out to be much, much larger than the original charge plus Q. But much larger, but it will be negative. So I put it in modulus, so to indicate that this is just a magnitude of the charge, not the sign of it. The magnitude of this negative charge will be much, much larger, hundreds and thousands times larger than the original charge placed here plus Q on the first small ball. So by using this small original charge, we may obtain much larger charges on other bodies using this procedure. And this idea is implemented in Van de Graaff generator. Van de Graaff generator, you can read about it in detail in your textbook in physics. It's described there. Van de Graaff generator allows obtaining huge charges of hundreds of thousands and even millions of volts when you have the initial charge very small, just like one kilovolt, for example, here. And here we can obtain about up to million volts. And the limit of charging, can this charging continue forever, and can we obtain infinite charges? No, certainly not. There is a limit. There is a certain physical limit to charging this body. We may obtain very large charge, but anyway not infinitely charged, not an infinite charge, and not an infinite potential. The potential will be limited by one physical effect. If the potential of this sphere is very large, there will be a lightning coming from here to the ground, and it will discharge finally. The lightning through the air, because air will conduct this large current from the highly charged body. Another thing I wanted to consider is problem 402. Can two lightly charged balls be attracted to each other? Good question. So we have two balls lightly charged, that is the idea, like charges, the charges of the same sign, for example, both positive. We have two balls positively charged, and we know that these two lightly charged balls must be repulsed from each other by some force of repulsion, which will be given by the Coulomb law. If this charge is plus Q and this is also plus Q, then it will be given by Q squared over R squared, where R is the distance between the centers of these two balls. So we know that lightly charged bodies repel each other. And the problem asks, is it somehow possible to observe attraction rather than repulsion of two lightly charged bodies? The answer is yes. Yes. The nature is not so simple as it seems at first sight. Let's consider non-charged metal sphere. So initially its charge is 0. And another sphere, well, I will put it here like positively charged. Positively charged. This is a positive charge, and here the charge is 0. What will happen in this case? If this is a conductor, the electrons will be attracted to the positive charge, and so that this side of the ball will be charged negatively, and the opposite side will acquire some positive charge. In this case, the negative charge will be attracted to the ball and to this positive charge, and the positive charge will be attracted to this negative charge. At the same time, this positive charge will be repulsed by this positive charge because lightly charges repel. But this repulsion between two positive charges will be smaller than the attraction between positive and negative charge, because the distance here is smaller. This distance r is smaller than the distance capital R between the charged body and these charges on the opposite side of the sphere. This distance is larger. So the repulsion from the positive charge will be smaller than the attraction to the negative charge. Therefore, such a charged ball will be attracted to the sphere which initially was not charged at all. The charge was 0. The charge was 0. And there will definitely be some attraction. And this polarization of charges, this separation of charges, negative and positive, is called polarization. The sphere will be polarized, and it will actually act as a dipole. Dipole is just like this distribution of charges when you have negative charge and positive charge, and this object will be a dipole if the two charged bodies are connected. So the sphere, conducting sphere, will become a dipole, a polarized sphere, and it will certainly be attracted to the ball, and the charged ball will be attracted to the sphere with some non-zero force. Non-zero force. What happens now if we put some small positive charge here on this sphere? very small. If this charge is very small, then the attraction between these two bodies will become smaller, but it still remains the attraction. If we increase the positive charge put on this sphere, then the attraction will become even more smaller, but it still remains an attraction. And we must put here some non-zero charge, positive charge on the sphere, so that there will be no attraction and no repulsion, and the force becomes zero. So before we reach this maximum charge, before we put a big charge on the sphere, if we put just a small positive charge, then the sphere will be positively charged, and still there will be an attraction between these two bodies. So two likely charges will be attracted. Two like charges, two positive charges will be attracted because one of them will be polarized and actually act as a dipole, as electrical dipole. That's the answer to this problem. Another thing I would like to consider, problem number 413, and that one was 4.2. That was problem number 402. And now I would like to consider problem 413. The point electric charge plus Q is at a distance d from a large conducting plate. So this point charge is placed at a distance d from a large conducting plate, infinitely large, so large that we can consider it infinite. Find the force with which the plate acts on the point charge. Find the force of interaction between the point charge and the infinite plate, such as the problem 413. So, what happens here? If this is a positive charge, then it will attract negative charges, and negative charges will flow here from the far ends of this plate. So here we will have some distribution of negative charges, and therefore the positive charge will be attracted to this surface, negatively charged. And negative charges will flow here because this is a conductor. This is a very large conducting plate. Very large. I don't even show the ends of this plate. The ends are far away. So that we may consider this conducting plate to be almost infinite. How to calculate the force of interaction between this point charge and the conducting plate, infinite conducting plate, if the distance between them is d? In order to figure out how to solve this problem, I will remind you about the field lines which exist between two unlike charges. If we take a positive charge, point charge, and negative point charge, then the field lines will be as we have discussed last time. The field lines will be like this, and so on, and so on. So the field of two unlike charges is well known if these two charges are point charges. And looking at this picture, you may understand that this picture is symmetric. The field lines are symmetric with respect to such vertical line, which is perpendicular to the section connecting, perpendicular to this line connecting the two point charges, and goes through the center of this section. So this plane is the plane of symmetry. All the lines will have the same form to the left and to the right of this flat surface. So that At this surface, all the field lines will cross it at right angle. So this will be angle of 90 degrees. If you draw a tangent line to the field line, a tangent, then the tangent will be at angle 90 degrees to the surface of symmetry. Now what will happen if we insert here an infinite conducting plate, a very thin one, very thin infinite conducting plate? What will happen? Will the field lines change somehow? No, they will not change, because we know that the field line must always be perpendicular to the conducting surface of the conductor. All the field lines must be perpendicular to the surface of the conductor. And that condition will be observed here. So if we insert here at the center between the 2 point charges an infinite conducting plate, it will not disturb the electric lines, the lines of electric field, the force lines of electric field. So what happens here, we understand now that the lines of field will go in this way. And they will be perpendicular to the surface of the conductor. And these lines of fields will look just the same as if we had some negatively charged particle placed at the same distance d from the conducting surface. So the lines of field will have the same configuration, whether you have a conducting surface here or you have no conducting surface and the 2 point charges each separated by distance d from the central surface. So the configuration of force lines of the field, of electric field, will be the same. That makes it possible to understand that the force of interaction between this charge and the surface will be the same as the force of interaction between this point charge and this point charge minus q, distance which is placed at a distance 2d from the initial charge. So the force of interaction will be k q squared. I used here a notation of capital Q. Okay, let it be capital Q squared here. Again, also must be capital Q. Q squared divided by 2d squared. So it will be k q squared divided by 4d squared. That will be the answer. That will be the answer to this question. The question was, what will be the force of interaction between the point charge and the conducting surface if this conducting surface is infinitely large, and if the distance between the point charge and the conducting surface is given and equal to d? What will be the force of interaction? That will be the force of interaction, and the coefficient here, you know well that in the international system it's 9 times 10 to the 9th power. International system. So if you measure Q, if you measure charge in coulombs and distance in meters, then using this coefficient you will obtain the force measured in newtons. That's the solution of this problem. And the method we used here, the method of field configuration, which is not changed if you insert a plane conducting surface here. This method is called the method of mirror imaging. That is because we actually used the mirror image of this charge. This is minus q, charge minus q is the mirror image of the upper charge in this surface, which is considered to be a mirror. So the method of solution is called the method of mirror images. consider problem, another problem 409. Problem 409. Two large conducting plates are arranged parallel to each other. So we have two conducting planes, two conductors, two plates arranged parallel to one another. The distance between them is much smaller than their dimensions. This distance is much smaller than their dimensions. Why this condition is given? It's given so that we could consider this an ideal flat capacitor. We don't have to consider the edge effects which emerge here at the edge of these plates. We may consider only what happens in between the parallel plates and disregard the edge effects. So the distance between them is much smaller than their dimensions. That is an ideal capacitor. One of the plates is given a charge plus Q. So we put charge plus Q here on this plate. And we do nothing with the second plate. What are the charges induced on the surfaces of the other plate? What are the charges induced? So if this is a plus, if this is a positive charge placed on the first plate, then it's obvious that electrons will be attracted to this surface, and this surface will be negatively charged, and the opposite surface will be positively charged. And we need to find what charge will be here, minus Q, and what charge will be here, plus Q. Induced charges on two surfaces of the second plate. We need to find this quantities. So, what do we know exactly in this problem? What do we start from in the solution? We know exactly that inside the conductor the field is zero. The electric field here inside the conductor is certainly zero. We know this for certain because in electrostatics the electric field does not go inside the conductor. And if this is a metal plate, the field inside it is zero. All the electric field occupies the external space and not inside the plate. No field inside the plate. This we know for certain. Whatever fields are outside, the inside field is zero because this is a conducting plate. Okay. Also we know that the larger the size, the larger the quantity of charge is concentrated on the surface, the larger will be the strength of its electric field generated by this charge. And the electric field here generated by this charge, and also the larger the charge on this surface, the larger will be the electric field generated by it. It will be directed to the negative charge. And let's call this field as E1, and it will be generated here also E1. And the field generated by this charge on the opposite surface will be E2, and inside it will be directed away from the positive surface, E2 inside. So each surface charged will produce some electric field. The positive charge will produce electric field directed outside the charges, and the negative charge will produce the electric field directed towards this negative charge. And we know that the resultant field inside the conductor must be 0. So the resultant field, that is E1 plus E2 must be 0. If we take vector E1 plus vector E2, the resultant field, the net field here inside must be 0. That's for certain. I'm not quite right here. I made a mistake because I did not take into account another field generated by this charge. This charge is here on this plate, and it will also generate its own field, which will go to infinity, which is the field E, and we must take it into account. All the three fields inside the second plate must produce 0 field. If we take into account only 2 fields, that will be not enough. There are 3 fields here. And also we know that the electric field strength generated by a surface charge is proportional to this surface charge, and for each charge. So the electric field E1 is proportional to the charge minus Q, which is accumulated on this surface. And if it's proportional, we just introduce some coefficient of proportionality, like alpha, and we may write that E1, the field generated by the left surface of the second plate, is proportional to the charge Q1, which is located on the left side of this plate. And the field E2 is generated by another side of the plate, is proportional with the same coefficient of proportionality, is proportional to the charge on the second plate. And also the electric field E generated by the first plate is proportional with the same coefficient of proportionality to the given charge placed on the first plate. So we have these conditions connecting the electric field generated by each surface charge. And now we can use the condition for the 0 field inside the conductor, 0 field, electric field inside the second conductor, and the relationship between the fields and the charges on the surfaces. And we will take into account the direction of each vector. So let's assume that positive direction is to the right. All the vectors looking to the right will be positive, and all the vectors looking to the left will be negative. So what we have here, in this case, E1 equals alpha Q1, and it's directed to the left, and so this must be negative. E2 is also directed to the left inside the conductor, so it will also be negative, and it must be proportional to alpha Q2. And the field E generated by the left plate is directed to the right, so it will be positive, and it will be defined by alpha capital Q, and all this sum must be 0. Also, we may understand that if some electrons were attracted to the first plate, and if some electrons went here to create the surface negative charge, then the same charge will be created, will be left, the same positive charge, the same by magnitude, will be left on the opposite side, on the opposite. So that these two charges are equal in magnitude. Q1 is equal in magnitude to Q2. So these are two equal charges that we may write like 2 alpha Q, that is the charge Q, generated on either surface, plus alpha capital Q is 0. From here we understand that alpha may be cancelled, and small q will be equal to large Q divided by 2. So we have solved the problem. What charge will be generated on the left side of the plate, of the second plate, minus capital Q divided by 2. And what charge will be generated on the right surface, on the right side of the plate, plus capital Q divided by 2. That's the solution of this problem. Oh, very good problem, 415. Which is a continuation of that Van de Graaff problem. Well, I will leave this picture here of the Van de Graaff generator. So we already discussed that we can charge this large sphere to a very large charge, but it will be limited if we obtain a very large potential. Then some effect which is called a puncture will occur, and the light and some charge will go away from the sphere, because all the charges are repulsed from each other and the force of repulsion is very large, and some charges actually will leak away and will accelerate. Some charges will accelerate and they will ionize the air, the molecules of air, and in this ionized air, the ionized air is a good conductor, and the good conductor will conduct the current, and this will be like a lightning, like a spark, this effect is called puncture, and the puncture on this light, or this lightning, will immediately reduce the total charge of the sphere. So this effect will limit the upper, will define the upper limit of possible potential which can be accumulated on this sphere. And problem 115 of problem 415 is related to this problem, to this puncture effect. It says, what potential can an isolated metal sphere with a radius r, so we have an isolated metal sphere with radius r, and it asks what potential can be accumulated in the air if the intensity of the electric field that causes a puncture in the air, the intensity of the electric field that causes a puncture in the air is 30 kilovolts per centimeter. 30 kilovolts per centimeter. So if we have a potential difference in the air 30 kilovolts per centimeter, then this air interval will be punctured by an electric discharge, and this small lightning, small spark will go through the air, and some charge will flow away from the sphere if we obtain such potential. So what will be the maximum possible charge obtained here, or maximum possible potential? The potential of a charged sphere is known to be Q over R, and the electric strength near the surface, if the sphere is charged positively, then the electric field strength will be directed away from the center of the sphere, and it will be given by the Coulomb law, which will give us Q over R squared. And that is obvious that the electric field strength can be expressed as sphere potential divided by R. And so the maximum sphere potential, maximum, which can be obtained in such an experiment of increasing the charge of the sphere, the maximum U will be given by R times maximum E, maximum possible field strength in the air. This is given in the problem. This is maximum possible field intensity. So the maximum potential will be given as radius times 30 kilovolts. For example, if radius is equal to, well, say 10 centimeters, then we obtain here 3 times 10 to the 4th power in the international system by 10 centimeters, which is 0.1 meter, and that will give us 0.1 meters, 3,000 volts. That will be maximum possible potential, after which the 3,000 volts, after which we will have the possibility to puncture the air, and some electric discharge will occur, and little sparks will appear here, and the charge will leak out of the sphere, and we will be unable to place more and more charge here, and we will be unable to increase the potential. The charges will become leaking. The process of leaking charges from the surface of the sphere will begin in this case. So, as we have a sorry, there is something, yes, there is something wrong in this solution, in this answer, because we are given 30 kilovolts per centimeter, and we have to take into account that this is not a meter, this is a centimeter. This is 30 kilovolts per centimeter. Certainly, I have forgotten about it, and 1 centimeter is 10 to the minus 2 meters, and we have to use only in the final answer, we have to use only the units of international system. And so 10 to the minus 2 in denominator will give us 10 to plus 2 in the nominator. And so the maximum possible potential will be 100 times more than what I obtained here. See, I was a little bit surprised that such a small potential was obtained in this problem. Actually, it will be 100 times more if we take into account that here we have centimeters rather than meters. And so the final answer will be 300 kilovolts. Yes, that looks like closer to reality. If we have a sphere of 10 centimeters in radius, then the maximum possible potential in the sphere will be 300 kilovolts. That looks like reality. Yes, that's closer to reality. Well, on this point, we have come to the end of this lecture. Let me conclude it, and goodbye till next time.